Today, I want to demonstrate the law of large numbers by replicating this plot on page 82 of the book. This plot is showing the proportion of rolls that it resulted in 1 for n dice, where n ranges from 1 to 100,000. You see n is the x-axis here, and the proportion of ones is on the y-axis. The law of large numbers says that if we repeat a random process over and over, the proportion of times an event occurs tends toward the probability of occurrence. This is how we define probability. Rolling a die is the random process. We're going to perform the process n times for n from 1 to 100,000. As n gets bigger, the proportion of ones we get should get closer and closer to 1/6, which is this line on the graph. You can see that when the number of rolls is low, the proportion of ones varies from this line quite a bit. But as n gets bigger, the distance it swings from this line gets smaller and smaller. Recall that in R, we can simulate rolling a die with the sample command like this. This 1:6 is telling it to choose from the integers from 1 to 6. This number is telling it how many dice I want. If I want 2, I can have it be 2. If I want 3, I can have 3, and so on. And we need to set replace equals true because it's set to false by default, and we want to be able to choose from all 6 numbers every time. I'm going to roll 1,000 dice and store the result as X. Control Enter. So now X is 1,000 die rolls. If I use this notation here with 2 equals signs, it will perform a logical test. It will give me true for every roll that was a 1 and false for the rest. Now, R considers true to be 1 and false to be 0. So this thing can be thought of as a vector of 1s and 0s. If I sum it, it will tell me how many trues there are. 165. Length tells me how many rolls there were. If I divide this count by the number of rolls, I get the proportion of times the roll was a 1. It's pretty close to 1/6, which is 0.167, and that's what I'd expect if I rolled 1,000 dice. About 1/6 would come up 1. Remember that sum divided by length is the same as the sample mean. I can get the same result with the mean command. And this is something we'll see again. If your data is all 1s and 0s, then the mean of that will give you the proportion of 1s. If I have X, B, C, 1, 1, 0, and then take the mean of X, that's 2/3, which is the proportion of 1s in X. First, I'm going to set a seed so that we'll all get the same results. I'm going to roll n dice for n equals 1 to 10,000. The book went up to 100,000, and you can if you want to, but the computer I'm on is really slow, and it took 10 minutes to complete this when I tried it with 100,000. So I'm just going to do 10,000. I make a placeholder vector called dice. This will hold my 10,000 proportions. For now, I'm going to fill it all with zeros. Rep 0 10,000 is saying repeat 0 10,000 times. And you can see in the upper right here that I have this vector of 10,000 zeros. Here's the syntax for the for loop. I say 4, then in parentheses, I in 1 to 10,000. That's going to let the letter I range from 1 to 10,000. Then a bracket, and inside the brackets, I do what I did before. I roll I dice. But then I find the proportion of ones and store it in the ith position of the dice vector. So when I run this, the first position of the dice vector will be the proportion for one roll. The 10th position will be the proportion for 10 rolls. The 1000th position will be the proportion for 1000 rolls, and so on. We're rolling I dice, where I ranges from 1 to 10,000. Let me run this, and we have the red sign down here. It's running. You can press this if you want to stop, but it looks like it's done. We now have 10,000 proportions. We can examine them using this square bracket. So the first element would be dice 1, which was 0. The 10th element would be dice 10, which was 0.3. The 30th element, when we rolled 30 dice, gave us a proportion of 0.1. The 7,645th element was with that many dice, and that was the proportion. If you want to see several proportions at a time, you can specify a range like this. To plot this thing, I want the number of rolls on the x-axis and the proportions on the y. The proportions are in dice, so dice will be the y-axis. The number of rolls goes from 1 to 10,000, so I'll just make a sequence going from 1 to 10,000 by ones, and that'll be my x-axis. So this is the x, this is the y. And I'm specifying type equals L because I want a line graph like the book has. By default, it will give me points. Notice that our graph settles very quickly. That's because the proportions settle near 1/6 very quickly. And this graph is mostly of n, where the proportion is close to 1/6. If you look at the book, their axis is on a log scale. It goes from 10 to the 0, 10 to the 1, 10 to the 2, 10 to the 3, 10 to the 4, and 10 to the 5. Those are powers of 10 evenly spaced. That's what I mean by a log scale. We can do that in R with the log argument in the plot. Here, I'm saying make the x-axis a log scale. And that looks a lot more like what the book had. I'm going to recolor this and change the labels. And finally, I can add this AB line argument. If you already have a plot, this command will add a line to it. I'll put it at h equals 0.167, and I use this LTY argument to make it a dashed line. And that's how to draw a version of the graph of the dice proportions on page 82 of the book. It's an important concept, and the techniques we used to construct the plot were important as well. We will be seeing more of them. One final thing, I set up a general version of the loop down here. If you wanted to experiment with more or less than 10,000, you can set it up like this, where you store the number as n, then base everything on n. That way you only have to change this one number, instead of having to change all the 10,000s you see here in the other code.